This is number 52 in chapter 16. It's a two-part question. It doesn't have a part A or part B. It's basically a run-on question here. I'm going to solve the first part of it, and then you should be able to use this example to solve the second part. So the first part talks about a 100 milliliter buffer solution, and that buffer solution contains 0.1 molar ammonia, or NH3, and then also has 0.125 molar ammonium bromide. And so that's a salt. So basically we have a buffer, right? Because we have a conjugate acid and we have its parent base. The question asks us what mass of hydrochloric acid will neutralize by the buffer before the pH falls below 9. So we're asked what mass of HCl and we're looking at this pH of this buffer to then reach 9, right? So once it falls below 9, so that's kind of our threshold, so that's what we're going to use for our pH. Then the question goes on further, but again, just with different concentrations, or I'm sorry, different concentrations. But what we see here in the first part, we should be able to use then in the second part. So first off, we always have to write the equilibrium for the buffer in terms of the parent, in this case a parent base. So ammonium reacts with water and make ammonium ion and hydroxide. So we have these two concentrations of our conjugate acid as well as our parent base. So we have a buffer situation, and so basically what we're trying to do is figure out what's the threshold for this pH. And so since our equilibrium equation involves hydroxide, that means we really should be looking at a POH, right? And so remember, that's just 14 minus our pH, and so that would be a POH of 5. If we look at the Henderson equation, Henderson-Hasselbalch, our POH is equal to our pKb plus the log of our conjugate, in this case ammonium, over our parent ammonia. And so we can rearrange this equation to basically solve for this new concentration of NH4. So if we start to plug in our values, we would have a POH equal to 5. That would be equal to our pKb, and so we'd have to take the negative log of our Kb. Now our Kb we're going to have to get from a table. So that 1.76 times 10 to the negative fifth comes from the Kb table, and then we would take plus the log of basically again this ratio NH4 to NH3. If we go a little bit further, right, our 5 equals the negative log of our Kb, and that value is 4.75. And so that's going to be then again plus the log of that ratio of conjugate to parent. So we need to rearrange this a little bit, right? And so if we bring the 5 and the 4.75 to the other side, right, and then get rid of the logarithm, right, you would be talking about this ratio, which would be equal to 10 to our POH minus that pKa. So I took the 4.75 over to the other side. That's where the 5 minus 4.75 comes from. And then I got rid of the logarithm by taking base 10. And so that's where we're at right now. Now, once we're there, I'm just going to make some more room here. So we're coming from this step, and we're coming up to some more space here. What is the ammonium concentration? What is the NH3 concentration? Right? We already have two concentrations for those two species of the buffer. So our ammonium concentration, right, is going to be 0.125 plus some change, right? Because if we're beginning with a buffer of NH3 and NH4, we don't really have any hydroxide yet. So our equilibrium is going to shift to the right. So there's going to be a positive change. Another way to think about that is, since we're adding hydrochloric acid, right, we're going to be converting our NH3, which is a base, into its conjugate acid by being reacted with hydrochloric acid, by neutralizing that proton source. So that's why we'd have 0.125 plus X for our NH4. For our NH3, we would have that 0.1 minus X, and so that is going to equal this 10 to the difference of our POH and pKb, and that value is 1.778. At this point, it becomes an isolation of X, right, and trying to get at X on one side and solving for it. If we bring over our 0.1 minus X to the other side, sorry, let's make some more space. So I brought over my 0.1 minus X to the other side, and I've actually then multiplied through. And so that gives us this. And so we begin to isolate terms. I'll bring over my X to the other side, and I end up with 2.778 X, which is equal to 0.0528, and if I solve for that, my X is equal to 0.0242 molar. So that is the change that I have to affect by adding HCl to change our initial concentrations of NH3 and NH4, the components of the buffer, so that now the pH has been skewed. It's been drop to a pH of 9. So with that value, it becomes a conversion. So we have our 0.0242 molar, or moles per liter. We're going to be in a volume of 100 milliliters, or 0.1 liters, and that would give us moles of HCl required. And then if we use the molecular mass of hydrochloric acid, we can get that into grams. And so we get 0.088 grams of hydrochloric acid added. So that's how you can use the pH in order to determine basically how much of an extra acid, or extra base for that matter, is added to a base. And so in order for this pH to reach 9 for this buffer, we would have to add about 88 milligrams of hydrochloric acid. And that's number 52, part 1. Again, I would try part 2. It's pretty much the same methodology.